Yep. So this talk stems from a paper that I wrote 12 years ago with Liang Dai and Donghui Zhang. And Liang was a graduate student at Johns Hopkins at the time. Donghui was a postdoc, and like all of my students and postdocs, they are above average. And so we did some very nice work. And I have to say, the paper, the total angular momentum paper, on which this talk is based, although not entirely just on this paper, is a very, very long paper with lots and lots of equations. And I was really proud of ourselves for writing this paper, and I thought it would be incredibly useful. And we put it on archive, and then I started to wait for all the citations to come in. And 1 month passed, nobody cited. I thought that's okay because it's a long paper, it takes a long time to read. 2 months passed, nothing. 3 months, nothing. And then about half a year later, there was a citation. Like, hey, we got a citation. So we went and looked, and it turned out that the paper had been miscited. And for the first and only time in my life, I had to send a please don't reference me email request. So anyway, the basic idea is that we developed a mathematical formalism that we call total angular momentum waves. From the point of view of mathematics, it's not that sophisticated, but it is a little more in terms of equations than we often have in cosmology. But the point is that there is a lot of machinery that's built into this formalism that we usually wind up doing anyway, and when we calculate, make predictions for cosmological observables. And by putting all of this complicated stuff that we always reproduce in every paper in a single formalism, this total angular momentum formalism, every other paper, if you understand how this works, that you write can be simplified in many different ways. So I'm going to start by reviewing Fourier analysis, which I'm assuming you all know. So in Fourier analysis, you can take any function f of x and sum over Fourier modes, all wave numbers k. So 3 spatial dimensions, that's a wave vector. So you sum over all possible wave vectors, f of k e to the ikx. And then you can do the inverse Fourier transform. The Fourier transform f twiddle of k can be written as the same sum, except you now flip the sign e to the minus ikx. So the reason, and I should say e to the ikx, these are plane waves. So this is a plane wave expansion of any function that you can imagine. And the reason why we do this is that these e to the I k dot x, these plane waves constitute a complete orthonormal set of basis functions for functions f of x that will live in 3 spatial dimensions if you're working in 3 spatial dimensions. So these e to the ikx are a complete orthonormal set of basis functions for scalar functions on R cubed. And that's why whenever we do cosmological perturbation theory, we always expand things in terms of Fourier modes for 2 reasons. First of all, it's easy. We all know Fourier analysis. And the second reason is that when we work to linear order in the amplitude of small perturbations, in the limit of small amplitude of perturbations, the equations of motion for the amplitudes of the different Fourier modes wind up decoupling. So we wind up with a set of differential equations for the evolution of amplitudes of Fourier modes. So that's why we use Fourier modes in cosmology. However, anyone who's ever written or looked at a paper on the cosmic microwave background or predictions for pulsar timing arrays knows that ultimately we take a plane wave, which is something that just goes in some particular direction, and then we project it onto a spherical sky. And so what happens is we have Fourier modes that are plane waves, but we want to have predictions on a sky that are statistically isotropic. And so we wind up projecting a plane wave onto a sphere, and we wind up getting these spherical Bessel functions and complications and things like that. The point of the total angular momentum formalism that I'm about to tell you about is that the spherical symmetry of the observed universe of the sky, the celestial sphere, is built into the formalism from the start, so we never have to project onto the sphere. We start by working in a spherical basis. Now, what else? The Fourier modes, e to the ikx, are solutions of the Helmholtz equation, del squared plus k squared f of x, and e to the ik dot x, these Fourier modes are eigenstates of spatial translations. So there's a spatial translation operator, and e to the ik dot x is an eigenstate of it. Now, oftentimes in cosmology, we will deal not only with scalar functions, but also vector functions. So for example, the velocity field, peculiar velocity field of galaxies, is described by some vector valued quantity as a function of three spatial coordinates. And again, we can Fourier transform a vector field. We can expand it in terms, again, of all Fourier modes k. And then for each Fourier mode, there are going to be three different polarizations alpha. So here, epsilon alpha is one of three polarization vectors. And we can have we can have two polarization vectors that are transverse to the direction of the vector of the mode. So if k is going in this direction, okay, the Fourier transform of a vector field involves a sum over all wave numbers k, or wave vectors k, and for each wave vector, there's a sum over three polarization modes. Two polarizations, 1 and 2, are transverse to k, and the third polarization is k itself, the longitudinal polarization. So for example, if I'm describing the electric or magnetic field associated with an electromagnetic wave, I use only the two transverse polarizations. If this V is a peculiar velocity flow, which is a potential flow, I need only the longitudinal polarization. And likewise, very often in cosmology, we deal with tensor fields. So for example, a gravitational wave is a tensor metric perturbation. So we do have tensor fields, HAB, which have two indices as a function of x. And here I'm not doing space time, I'm just doing space, three spaces. So A and B go from 1, 2, and 3. They are x, y, and z. If you are thinking of this as a space-time metric perturbation, though, this is the space-time metric perturbation in synchronous gauge, where the zero components are set to 0. And in this case, if HAB is a symmetric tensor field, then most generally there will be 6 polarization vectors, S. So for each Fourier mode K, there are 6 polarization vectors S, and they can be taken to be the trace of the metric, the longitudinal component. There are 2 vector modes that are transverse, and then there are 2 modes plus and cross, which are the 2 transverse traceless modes, which are the modes that account for gravitational waves in general relativity. So it's something similar. We can always, there's nothing that complicated about it. Now, total angular momentum waves are an alternative set of basis functions, an alternative complete orthonormal set of basis functions for scalars, vectors, and tensors in 3 spatial dimensions. Now, they are again, like the Fourier modes, eigenstates of del squared plus k squared psi. So they are described by a quantum number k, which is the same as the magnitude k of the Fourier mode that we dealt with before. But then these total angular momentum waves, instead of being eigenstates of spatial translations, these are eigenstates of rotations. And eigenstates of rotations are parameterized in terms of quantum numbers j and m. Angular momentum quantum numbers j, total angular momentum quantum number j, and an azimuthal quantum number m. So as I said, the symmetry of the celestial sphere is built into this formalism. We have total angular momentum waves for scalar, vector, and tensors. For scalars, it turns out to be very easy, almost trivial. So the scalar total angular momentum waves are these things that I call capital psi. They have 3 quantum numbers, which I just realized throughout the rest of the talk I'm using L and M. So the basis functions in this case, these total angular momentum waves, have 3 quantum numbers k, which is analogous to the magnitude k of a Fourier mode. And then we have, instead of a direction of a Fourier mode, we have angular momentum quantum numbers L and M. And it turns out that the scalar total angular momentum wave is simply the product of a spherical Bessel function, J sub L of Kr, times a spherical harmonic. And this actually appears in the literature all over the place, well, in various places, and it's often referred to as the Fourier Bessel expansion. And there's not a whole lot of profitability by dividing total angular momentum waves for scalar modes because this is so simple. Things, though, get more complicated and more powerful when you go to vector and tensor fields. So the vector total angular momentum waves, again, have quantum numbers K, L, and M, but there is also there are also three different types of total angular momentum waves that correspond to the three possible polarizations. So for the Fourier modes, we take the polarizations to be two transverse modes and a longitudinal mode. In this case, we take them to be a longitudinal mode. And then there are two other modes, which we call E and B. And I'm not going to go through those in detail, but I will say a little bit more about the tensors. So for the tensors, the total angular momentum waves, again, have these quantum numbers K, L, and M. There are these tensorial indices A and B, which go from 1, 2, and 3. And S here are the polarizations. And again, there are 6 different types of polarizations, but rather than being longitudinal trace vector, the two transverse vectors and the plus and cross, we have 6 other polarizations. And for the purposes of this talk, I will mention only the 2 polarizations that correspond to the transverse traceless or gravitational wave parts of the perturbation. So instead of having plus and cross gravitational waves in this formalism, we have what we call TE for tensor E and TB for tensor B polarizations. Okay. So keep in mind, these are not the E and B modes of tensor valued functions that live on the surface of a sphere, which are what we usually consider when we talk about the cosmic microwave background. These total angular momentum waves are functions that live on 3 spatial dimensions and have 3 spatial dimensions themselves. So these are 3 by 3 tensors that live in 3 spatial dimensions. So this paper was written about 10 years ago. I told you we waited the longest time for a citation and nothing happened. And then, you put those other papers on, you're like, should we even publish this? No, this is an embarrassment. And then you put it on the archive and then everyone cites it. Anyway, since then, though, we have been able to use this formalism for a variety of different things in cosmology. And I have to say, there were about 5 years that passed when I didn't touch this at all. And then there were several problems that showed up that just seemed like they were designed for the total angular momentum formalism. And so we followed through. So I'm not going to go through in order of the work, but I'm going to mention several applications and also inspirations, because I should say that some of the work I'm going to tell you about does not really use the total angular momentum formalism, but I think were facilitated by tools that were acquired in the process of thinking about these kinds of things. So the applications I will talk about are in pulsar timing arrays and gravitational waves, and also several in cosmology. So first, I will start with pulsar timing arrays and gravitational waves. So as half of the audience knows, there is now an effort being pursued in this country and abroad to detect gravitational waves that have frequencies of about a nanohertz. And these gravitational waves, we know, have to be out there because we know that there are supermassive black holes, and we have very, very good reason to believe that at least a good fraction of the mass of these supermassive black holes came from mergers of lower mass supermassive black holes. And we have some idea about the number density of supermassive black holes. So we know to within, some uncertainty of about a factor of 10, what the amplitude of the local gravitational wave background due to supermassive black hole mergers should be at nanohertz frequencies. So there are a number of members of the nanograph collaboration here, which are the people who've been working really, really hard to make this happen in this country. And they collaborate then with a European PTA and an Australian PTA and something they call the IPTA, which stands for International Pulsar Timing Array. Good. I'm waiting for you to go like this.
Not yet.
Not yet. Okay. So it turns out that pulsar timing, the total angular momentum formalism is very, very good at recovering and reproducing some of the results that we have for observables for pulsar timing arrays. So the basic idea in a pulsar timing array, here's where I need two hands. So the basic idea of a pulsar timing array is that if there's a gravitational wave coming from that direction, and if there's a pulsar over there and a pulsar over there, and if that gravitational wave has a plus polarization, then this pulsar will be moving towards me while this one is moving away from me, and vice versa. And so what will happen is that the frequency of the pulsar, the pulse frequency, the spacing between the pulse arrival times will be smaller for this pulsar and larger for this pulsar. Now, it's difficult to actually measure precisely the arrival times of individual pulses, but if I can time this pulsar against this pulsar, I will see a variation in the frequency of this versus this with time. So there'll be a variation of the pulse arrival times coming from here and from here, and it will be such that when this one is moving away, this one is moving towards me. And I can do that for pulsars spread throughout the sky. And so I'm sensitive to gravitational waves coming from all directions on the sky and with both plus and cross polarizations. So that's how a pulsar timing array works. Now, the issue is that we don't have a gravitational wave that we know is going to be coming from that direction quite yet. What we're looking for is a stochastic background of gravitational waves. And so we can't say, I'm going to look at this pulsar versus this pulsar and just look for gravitational waves over there. What I have to do is measure the 2-point correlation function for the pulse arrival times, or the shift in the pulse arrival times for pulsars spread throughout the sky. So that is this famous Hellingsdown curve right here, Xi of theta. So Xi of theta is I call it redshift. Pulsar people usually call it the pulsar timing residual, but it's essentially the peculiar velocity of the pulsar as inferred from the pulse arrival times. The redshift of a pulsar in some direction hat n on the sky, and the redshift measured for a pulsar in another direction hat m on the sky, where n and m are separated by an angle theta. So to measure this 2-point correlation function, I measure the arrival times I measure the redshifts for all pairs of pulsars separated by some angle theta across the entire sky. So this can be calculated, and this was done first by Detweiler. Is that right? No. What's the guy's name? You should know.
But I'm just trying to give you some time.
I know. I'm just.
What do you mean by first? Because there was first the idea was for
Yeah.
right? Like it was for the
Yeah. Sorry. Yeah. Hellings Downs curve, but this came from. That's actually surprising. Usually you name it after whoever wrote it second. Possibly.
The Hellings Downs curve was originated by Hellings Downs in 1983, and Detweiler was in 1979.
Detweiler. Okay,
Yeah.
good. So I did get Detweiler right. Okay, good. Okay. So here's how the calculation works. So if the gravitational wave is moving in direction hat n, if the gravitational wave is moving in direction p, so the gravitational wave is moving in direction p, which I can take to be the z-axis if I want, then the redshift experienced by a pulsar in direction n is HAB, NA, and B, where HAB is the amplitude and polarization vector of the gravitational wave. So, for example, if I take P to be in the Z direction, this turns out to be proportional to 1 minus cosine theta cosine 2 phi, where theta is the angle between the gravitational wave direction and the pulsar, and then phi is the azimuthal angle. And so the cosine 2 phi here follows from the spin 2 nature of the gravitational wave. So you then calculate this, and then you take an average over all possible gravitational wave directions, you average over all pulsar positions on the sky, and then you average over the two the two gravitational wave polarizations. And the calculations are straightforward. They're in the literature, and they involve integrals. And the result is that dew-point correlation function calculated by Hellings and Downs first in 1983, I just learned, is, I probably knew that. I'm sure I knew that. I don't remember. It turns out to be x log x minus 1/6 x plus 1/3, where x is 1/2 1 minus cosine theta. So this is what they are looking for. And if I plot it, C of theta looks sort of like this. So here's C as a function of the angular separation between two pulsars, where this is 180 degrees and this is 0 degrees. So it peaks at 0, it then drops below 0, becomes an anti-correlation for larger angular separations. Now, it turns out that the total angular momentum formalism is ideal for doing this calculation in a simpler way. So the basic idea of the calculation, and here I'm just going to step through it to advertise because all the details, quite a few details. The basic idea is that this result here, the redshift of a pulsar in a direction hat n in the presence of a gravitational wave moving in direction hat p, comes about by doing an integral along the line of sight to a pulsar in a given direction in the presence of a gravitational wave or metric perturbation that has the form HAB of t as a function of t in space. And here this integral is taken along the line of sight to the given pulsar. So I integrate along the line of sight, and at each point along the line of sight, I evaluate HAB at that point and at that time that a photon or that would have passed by that point. So that is the line of sight integral that gives rise to that simple expression. And the idea behind the total angular momentum formalism is that any tensor metric perturbation, any collection of gravitational waves can always be written as a sum over total angular momentum waves, psi, KLMAB, where S is a sum over the the tensor E and tensor B, which are the total angular momentum equivalents of plus and cross. And then you look at equation 93 in our 2012 paper. And equation 93 in our 2012 paper, we have radial eigenfunctions for each one of these. So each one of these total angular momentum waves can be written in terms as a function of distance, r, and angles, theta and phi. And when we do things in this way, it's only the radial eigenfunction that we need to integrate over. And so what happens is that redshift for a source, a pulsar in direction hat n, just turns out to be a spherical harmonic times this radial eigenfunction. And it turns out that Mathematica can do this radial eigenfunction integral, and even I can do it without Mathematica. It turns out to be easy. And it turns out that it turns out that Z of hat n can be written as a sum over spherical harmonic coefficients. So Z of n, I should have written this. I thought I had it in here somewhere. I can always write any function of position on the sky as a sum over spherical harmonics times spherical harmonic coefficients ZLM. And so what this expression here is telling me is that the Z, due to this particular total angular momentum wave, is proportional to YLM. And so the thing that multiplies YLM over here is the spherical harmonic coefficient. So the spherical harmonic coefficient due to this gravitational wave turns out to be proportional to L minus 2 factorial over L plus 2 factorial for the TE modes. And interestingly enough, the TB modes contribute nothing. It's kind of interesting. When you use pulsar timing arrays to look for gravitational waves, you're only looking for half of the gravitational waves. We don't notice that in the plus cross formalism because plus and cross are the same, except apart from a rotation by 45 degrees. But in this total angular momentum formalism, it's clear that you're only detecting or sensitive to half of the gravitational waves. So the power spectrum, we then define a power spectrum, and the power spectrum is equal to the expectation value averaging over the stochastic background of the squares of the ZLM. And so we infer that the power spectrum for the pulsar timing array residuals is L minus 2 factorial over L plus 2 factorial. And then to get the Helling-Downs curves, we simply realize or note that the 2-point correlation function, which is the expectation value for the product of redshifts for two pulsars separated by angle theta on the sky, is equal to a sum over all L of Legendre polynomials, P sub L of cosine theta times these power spectra. And then if you plug L minus 2 factorial over L plus 2 factorial, there are a few lines of Legendre polynomial algebra that give you the Helling-Downs curve. So it turns out that in this way, all of the hard work that you often see in the derivations of the Helling-Downs curves is put into all the stuff that we did in this paper back in 2012. And if you know that, then this result sort of pops out. Now, I should say, we were really proud of ourselves because we wrote this paper where we showed that you can rederive this Helling-Downs curve in a far more economical way with this total angular momentum formalism. And there you have it. And then as we were preparing the paper, we realized there was an even easier way to rederive the Helling-Downs curves, which is an appendix C in the paper, which I can go through afterwards if anybody wants. Actually, I can tell you. So you don't need the total angular momentum formalism. So this is the pattern on the sky induced by a single gravitational wave propagating in the z direction with a plus polarization. So it's very easy, and it turns out to be 1 minus cosine theta times cosine 2 phi. Now, if you ask Mathematica, what are the spherical harmonic coefficients that correspond to 1 minus cosine theta cosine 2 phi, it will tell you that those spherical harmonic coefficients are proportional to L minus 2 factorial over L plus 2 factorial. And that is all you need to know. So that L minus 2 factorial divided by L plus 2 factorial, it does not matter which direction the gravitational wave is moving, because these C sub L's and the Helling-Downs curves are rotational invariants. So it makes no difference what direction the gravitational wave is propagating in. It also makes no difference what the polarization is. And for this particular physics, this is the distant source approximation that we always work in. In this limit, the frequency of the gravitational wave also doesn't matter. So any gravitational wave propagating in any direction with any polarization and any frequency is going to give me the same contribution to this angular power spectrum and the same Helling-Downs curve. So that's all you need to do. plug in, this is 1/2, it's 1 minus cosine theta, cosine 2 phi. Multiply that by spherical harmonics, integrate over 4 pi, and you get the answer. So that is the first application. In this paper, and I should say I have to advertise my collaborators. Wenzer Chin was an undergraduate when she did this, and she was like one of these people who like took the quantum field theory class when she was a junior and like did better than everybody else and better than anybody else since then who's taken the class when they were a junior. She's now a graduate student at MIT, and Kim Boddy is second author, is now a faculty member at UT Austin, and Liang Dai was, so actually this, well, long history. Liang Dai is now a assistant professor at Berkeley. Really? Oh, mazel tov. So, is she here? No. Okay. So in this paper, though, we also did something else. And the motivation for this work, although I just talked about pulsar timing arrays, was actually gravitational wave astrometry. So this idea goes back several decades, but I think that the paper that sort of put it on the map for many people was one by Laura Book and Anna Flanagan in 2011. And the idea is quite similar to that for pulsar timing arrays. With a pulsar timing array, if there's a gravitational wave propagating in this direction, there are going to be delays or redshifts in pulse arrival times. However, that gravitational wave will also shift the angular position of objects on the sky. So the gravitational wave distortion to the space-time metric is going to move the positions of stars and radio galaxies, everything on the sky. And so what you wind up looking for is a shift delta theta in the positions of stars or quasars or anything else on the sky as a function of position theta on the sky. And we do this for all 4 pi steradians in principle. And if you measure this quantity delta theta, and this is a 2-dimensional vector that lives on the surface of the celestial sphere, that 2-dimensional vector can be decomposed into an E mode and a B mode, where an E mode is the component of that vector field that is curl free, and the B mode is the component of that vector field that is divergence free. So it turns out that with astrometry, and so suppose you had a pulsar timing measurement of the redshift as a function of position, and we have this, no. Suppose in addition you had a super Gaia that could measure the positions of stars throughout the sky, or a good fraction of the sky, with incredible precision, and keep doing it every couple of weeks for a few years, then you would also be able to infer E of theta and B of theta. So we have with this combination of pulsar timing arrays and astrometry, we have 3 observables. We have the redshift, we've got the E, and we've got the B. And from these 3 observables, you can construct most generally 6 auto or cross correlation functions. There's the ZZ, the EE, the BB, the ZE, ZB cross correlation, and EB. These last 2 are expected to vanish by parity unless there's some type of parity breaking physics, for example, a chiral gravitational wave background. But if the gravitational wave background is composed of equal amplitudes of right and left circular polarized gravitational waves, we expect there to be only these 4 over here. So it turns out that with the total angular momentum formalism, we can derive expressions for the spherical harmonic coefficients for E and B, and they turn out to be exactly the same. The only difference is that this radial eigenfunction is a little bit different for E and B. And so what we find is that for the 2 standard gravitational wave polarizations, TE and TB, oh, I can't draw on this part. So for the 2 gravitational wave polarizations, TE and TB, This is the Hellings-Downs curves that I showed you before, where n sub l to the minus 1 is l minus 2 factorial divided by l plus 2 factorial. It turns out that there's going to be an E mode with a power spectrum that differs by a factor of L times L plus 1. And it turns out that the astrometry is sensitive also to the B modes, and that winds up having the same angular power spectrum as the E modes. The other thing that's interesting is that if you could do this astrometry and the pulsar timing array, so if I had a PTA map of the gravitational wave sky, I could predict precisely what that E mode map would see and vice versa. So the E modes of the gravitational wave astrometry measurement give you exactly the same measurement, exactly the same information as the pulsar timing array. The cross correlation between those two is 100, is the cross correlation coefficient is 1. And the B modes, though, can be accessed only with this astrometry. So if you had astrometry, you could verify the PTAs, but then you would also have information about this other half of the gravitational wave background. So a little bit about pulsar timing arrays. This really has nothing to do with total angular momentum waves, but as I said, some of the, I think I was thinking along these lines because of the total angular momentum waves. So the observables, as we said, are the redshift of pulsars as a function of the pulsar position on the sky, hat n, which is equivalent to the spherical harmonic coefficients, ZLM, through this relation and the inverse relation. So if you give me a map of Z of n at any given time, or for some fixed frequency, I can obtain ZLM and vice versa. So they're equivalent descriptions of the observables. Now, one of the things that people are interested in, and Chiara and her collaborators have written papers on, is the gravitational wave anisotropy. So if the local gravitational wave background is a bona fide stochastic background that's due to contribution of huge numbers of supermassive black hole binaries, then it will be statistically isotropic or close to it. If, however, the local gravitational wave background happens to be dominated by a handful of local sources, then it's easily conceivable that the local gravitational wave background could be anisotropic. And so it's interesting to ask whether we can test or look for anisotropy in the gravitational wave background. So one way you might want to do it is to parameterize the intensity of the gravitational wave background in terms of spherical harmonic coefficients, GLM. So for example, for capital L equals 1, that would be a dipole anisotropy, more gravitational wave power from that side of the sky than from that side of the sky. L equals 2 would be a quadrupole. The natural thing to focus on first would be a dipole, because that is probably what is going to be biggest if there is some type of anisotropy. But this is the most general expansion. And you can write down estimators for these capital GLMs from the observable Z of n. And for this, you should see papers by Chiara and collaborators. But in this paper that I wrote with Salim Hotinli and Andrew Jaffe, and where is it? Some year recently, guessing 2018, I think. We rederived the results that they had derived previously in configuration space using these harmonic space observables. So in this case, we work with ZLM instead of Z of hat n. And then it turns out that if you know how to add angular momenta in quantum mechanics, and I taught quantum mechanics, graduate level quantum mechanics for several years, and I don't think it was until I started doing calculations like this that I really understood what the point of Clebsch-Gordon coefficients is. But now I know what a Clebsch-Gordon coefficient is. So it turns out that it is straightforward to write down, I don't want that. So it is straightforward to write down an estimator for these GLMs from the spherical harmonic coefficients. And it turns out to be a very compact and elegant expression. And I don't think we've published it, but we have done work to verify that it's the same as what you have. And I think you have that in your paper with the recent papers with obscenity. Yeah. Okay. Um, Now, the other thing that I'm really proud of, because anytime I've ever had an idea to work on something with PTAs, I look through literature and I find that Chiara's already written the paper. But for the first time ever, we found something that Chiara had not yet written a paper about.
I was writing one on this.
Yes. I mean, I know. So it turns out that the exact same formalism that you would use to look for anisotropy, the exact same equations, can also give you estimators for the spherical harmonic coefficients for the circular polarization as a function of position. So again, if the gravitational wave background, local gravitational wave background is dominated by some particular binary over there, and that binary is face on or not perfectly edge on, the local gravitational wave signal is expected to be have circular polarization. And the circular polarization is expected to be a dipole because there's a signal from that side, but not from that side. So that would be described by a capital V with L equals 1. And so we modified the formalism in this paper, and it amounts to no more than changing a sign that was -1 to -1 to the L to -1 to the L minus 1. So there's certain odd parity Clebsch-Gordon coefficients that show up in the first estimator, and then even parity spherical harmonic coefficients that show up in the second estimator. So you can look for the circular polarization in that way. That was a paper with Enes Belgesem a few years ago. And then Gabriela Sato-Polito, who is graduate student at Johns Hopkins now, and I recently translated the results in this paper, which are in terms of these spherical harmonic observables, into configuration space. So we derived the expressions in terms of overlap reduction functions that PTA people traditionally work with. So that is all I have to say about pulsar timing arrays. What am I doing with time? Okay. So I'm going to finish with a few applications to cosmology, as well as something that has nothing to do with total angular momentum waves, but arose because of something that I was thinking about related to total angular momentum waves. So there are a number of applications of this formalism to cosmology. One of them, which is part of the motivation for our original work, is that it allows for efficient computation of 3-point functions, angular 3-point functions for theories with a given spatial 3-point function. So if any of you have ever looked at papers where they calculate the angular bispectrum for models in which there are gravitational waves with a non-zero bispectrum, those papers, you'll have to refill the ink cartridge on the printer after printing those papers out, because there's like a full cartridge worth of Wigner 6J and 12J symbols that have to be gone through. And it turns out that if you use the total angular momentum formalism, you will never in your life encounter anything more than a 3J symbol. And the basic idea is that if I have a tensor mode, a gravitational wave, that gravitational wave has a direction that it propagates, and under rotation of the coordinate system, that direction moves, but it also has a spin. And so under rotation, I also have to rotate the spin. And so when I talk about angular 3-point correlation functions, I'm actually talking about 6-point functions, because I have an angular momentum for an orbital angular momentum for the gravitational wave mode 1, and a spin angular momentum for the gravitational wave mode 1, and then same for gravitational wave mode 2 and gravitational wave mode 3. And so what you wind up doing in the naive calculations is adding not 3 angular momenta, but 6 angular momenta. And that's why you get this proliferation of Wigner NJ symbols. And in the total angular momentum formalism, you just write down the spatial 3-point function, and then there's a direct translation into the angular 3-point function. The second thing is kind of a novelty. Um, so I told you that with pulsar timing arrays, you do not detect the B mode components of the gravitational waves. You only detect half of the gravitational wave amplitude. It turns out that you can, although there's no good reason to do so, it is possible to construct a tensor metric perturbation with the total angular momentum formalism that would give you B modes in the CMB polarization, but no temperature fluctuation nor E mode polarization. So it's a sick situation because it violates the Copernican principle, but it is possible to construct the tensor metric perturbation in which we are at a special point such that we would not see any E modes or tensor or temperature fluctuations, but see only B modes. So that is that. The third thing, which is a little more recent, a little more interesting, is CMB circular polarization. So we never hear about CMB circular polarization because Thomson scattering, which is what creates polarization in the cosmic microwave background, creates linear polarization, but does not create circular polarization. So you never hear about circular polarization. But it is interesting to ask whether the cosmic microwave background could have a circular polarization in the standard cosmological model. That's non-zero, even if it's too small to detect. In principle, is it possible? And it turns out that Ray Sawyer, an atomic physicist at Santa Barbara, in 2014 wrote a paper that was then followed up a few years later by Montero, Camacho, and Hirata in a very nice paper where they showed that it is possible. Not only is it possible, there is a standard model prediction for circular polarization of the cosmic microwave background. Actually, they did not say that. They actually calculated the circular polarization from gravity. Actually, I've got to be careful because I don't remember. In fact, the paper focused on gravitational waves, but I don't think they actually it was clear from the paper that there was a standard model prediction. I don't know if they calculated it though. Anyway, so they wrote this paper, and the basic physics is as follows. So if I have a CMB photon that is traveling towards me, along the line of sight, that CMB photon propagates through a cosmic microwave background. So we see a cosmic microwave background, but at any point along the line of sight, there is a cosmic microwave background. And we see a cosmic microwave background quadrupole. The local cosmic microwave background intensity is not isotropic. And the same is in general true at any point in the universe along this line of sight. And so this photon, as it propagates along its way towards us, it sees a photon background that is anisotropic. And in electromagnetism, quantum electromagnetism, it is possible for there to be a photon-photon interaction that is mediated by an electron loop. So electromagnetism, classical electromagnetism has no light by light interactions, but there's a quantum correction that gives you light by light interactions. And so if this photon, as it's propagating along the way, sees an anisotropy, it is possible for there to be an index of refraction for this polarization state of the photon, and then a different index of refraction for this polarization state of the photon. And so if the photon is initially linearly polarized in this direction over here, now the electromagnetic wave is coming in your direction. If it's initially polarized in this direction over here, that polarization is a linear combination of this and this. But now the component along this direction is going to propagate a little faster than this one. And so now we'll have a linear polarization in this direction that's out of phase with the linear polarization in this direction. So this differential index of refraction can induce a circular polarization. And so it is a straightforward calculation to go through. And it turns out that the total angular momentum formalism allows you to obtain the result, do the cosmological perturbation part of the calculation much more efficiently. So it turns out that the rotational symmetry of a quadrupole that the photon sees as a function of position on the sky is built into the total angular momentum formalism. So you can write down equations. You can essentially guess what the equations have to look like. And then instead of doing a calculation, I looked at my result and then reversed engineered the Harada Montero Camacho result to figure out what the coefficient in front had to be. And that allows you to get the answer. It's a, okay, the result. I mean, the circular polarization is a pseudo scalar on the surface of the sphere. And I have this polarization quadrupole. And then I have the CMB linear polarization, which is described by this quadrupole. And there's only one thing that you can write down. And that turns out to be the answer. There's another interesting result that appeared in a subsequent paper by Keizuke Inomata and I. So Keizuke and I generalized this result for gravitational waves and vector perturbations to the space-time metric. And one of the things that's interesting is that people consider models in which the primordial gravitational wave background not only exists and is non-zero, but is chiral, which there's an excess of right-handed gravitational waves over left-handed gravitational waves or vice versa. And we were able to show that if that's the case, this interaction allows that chirality in the gravitational wave background to be transmitted to the photon background. So if the gravitational wave background is chiral, there is an excess of right circularly polarized photons in the cosmic microwave background versus left circularly polarized in the cosmic microwave background. It is ridiculously and embarrassingly and shockingly unobservably small, but it is interesting to note that if we have parity breaking in gravitational waves, there's also parity breaking in the cosmic microwave background.
So you can have parity breaking in the gravitational waves serve as a way mechanism for baryogenesis.
That's Stefan.
Yes.
That's his wheelhouse.
Right.
Yes. Yes, you can.
If you do that at the level Stefan wants, is that observable?
That will not give you an observable in this particular way, because this is post-recombination physics. Yeah, okay. Something similar for 21 centimeter. Now this, I'm just gonna, nothing here is that important. But I want to tell you that, so while at some point, I was thinking, I've never liked this Boltzmann hierarchy that we have when we have to calculate CMB fluctuations. It seems ridiculous that a photon which scatters through a Thomson cross section, which has only a quadrupole dependence, requires us to solve an infinite number of differential equations. And we have to do it not when the photon's scattering from electrons over and over and over and over, but the photon is just traveling. The photon, the late time propagation of photons. In order to describe the CMB power spectrum for that, we have to solve an infinite number of differential equations, which seems wrong. And it always seemed wrong to me. And to make a long story short, it turns out that each one of these infinite Boltzmann hierarchies that you need to calculate the temperature fluctuations of the cosmic microwave background can be replaced by a fast Fourier transform. So the idea is, just to tell you very schematically, instead of writing the Boltzmann equation as a set of an infinite set of coupled partial linear differential equations for different multiple moments L, you can write the equation for the L equals 0, which is all you need, as an integral equation. And one of the reasons we don't do this is that no one knows how to solve an integral equation, or not to solve it very effectively. But for neutrinos, it turns out there is a similar integral equation. But what's interesting for neutrinos is that the integral equation is not an integral equation. It's just an integral. And we know how to do integrals. Moreover, as Ling Yuan Ji, my student who's been collaborating with this noticed, the integral that we need to do is a convolution of two functions. And you can always evaluate a convolution is in Fourier space is multiplication. So all we need to do is Fourier transform J0, which is sine x over x, which you can do in your spare time. And this function over here, which FFTs are very good at doing. And so each Boltzmann hierarchy can be replaced by a simple FFT. And we believe, but have not yet demonstrated by actually going through the entire exercise, that it should be possible to speed up class. By how much, I don't know. If you have three massive neutrino species, the computational effort is devoted almost entirely to the neutrino Boltzmann hierarchies. And we can get rid of them with these FFTs. The only trick, though, is that we also have to solve evolution equations for the baryon perturbations and the photons and the dark matter. And so there are other, and the Einstein equations. So there are other differential equations that we have to also solve. But what we believe is that it can be done iteratively. So we've actually been able to show that this works. You can solve the other equations in the system, use the solutions for those to evaluate the line of sight integrals for the neutrino moments, and then plug those back into these equations. And we've done some numerical experiments to show that this iteration converges very quickly. And we're trying to actually make this happen. Just recently, we started collaborating with Julien Legords, who's the guy who wrote Class, and a student of his, Sven Gunther, and Ling Wanji, Jose Luis Bernal, and I. Well, I is the inclusive I, which means I sat in on the Zoom, the first Zoom. So we're actually trying to get this to work in class. And I'm hopeful that it might actually yield substantial results, but we won't know until we know. So I will stop.
So essentially out of time. We started a smidge late, so if there's a question that someone is burning to ask, Kiara, yes, go ahead. So you've given me a lot of credit throughout your talk, but for circular polarization, I just wanted to say that Cato and Soda in 2015 wrote down the overlap reduction functions, and Rio Cato is in the back of the room right there.
Yes, I forgot to say that. Yes.
That's okay.
Yes, so our overlap reduction functions agree with theirs, but we went a step further in filling out the
estimators, and yeah, that was awesome.
Okay.
I was wondering about the chirality of the background. I know that Bob Caldwell also looked at this. How can we, if there is a handedness in the gravitational wave background in some sort of primordial sense? In 2016, I looked at this with Paul Lasky and Tristan Smith and others about how you can constrain the gravitational wave background from these primordial sources over multiple decades. Would you expect that signal to be similarly constrained and propagate over all frequencies, or does the chirality break some of my intuition there?
We have no idea. It's easily conceived. I mean, I'm sure somebody could construct a model in which it was chiral on cosmological scales, not chiral Hertz frequencies. One thing that's interesting about this formalism, and I think it also came out of your work, is that you cannot detect a circular polarization monopole with pulsar timing arrays. We can detect circular polarization anisotropy, but if there's a monopole for the circular polarization, it cannot be detected with pulsar timing arrays.
That's really interesting.